So welcome to video 3 for lesson 3.2. This video will cover the chi-square distributions. Chi-square distributions are very important in the field of statistics. They are used frequently for hypothesis testing when we're doing statistical inference. One place you may have seen a chi-square test in a previous class is for testing for independence between two categorical variables. For instance, is hair color independent of gender? Another place you might see it is for testing goodness of fit of a model, and there are many other applications as well. The chi-square distribution is really just a special case of a gamma distribution. If we take our theta parameter from the gamma distribution and set it equal to 2, and we call alpha equals r over 2, where r has to be a positive integer, then r is called the degrees of freedom, and we say that x has a chi-square distribution with r degrees of freedom. Let's take a look at how we can find the chi-square probability density function, the PDF. Recall that the PDF for the gamma distribution was given by little f of x is equal to 1 over gamma of alpha. Remember, gamma of alpha is alpha minus 1 factorial when alpha is an integer. We multiply that by theta to the alpha, and then take x to the alpha minus 1 times e to the minus x over theta. Now, when we substitute theta equals 2 and alpha equals r over 2, remember r degrees of freedom, then we get that f of x for the chi-square distribution is 1 over gamma of r over 2 times 2 to the r over 2 times x to the r over 2 minus 1 times e to the minus x over 2 for values of x greater than 0. So chi-square distributions have to be greater than 0. We can see that they depend on the degrees of freedom. So there's not just one chi-square distribution. There are a whole bunch of different chi-square distributions, an infinite number of them, depending on how many degrees of freedom we have. Taking a look at a chi-square moment generating function, we'll see what form that's going to take. Again, remember from the gamma distribution, our moment generating function was m of t equal to 1 over 1 minus theta t raised to the alpha power for t less than 1 over theta. Again, we'll substitute theta equals 2 and alpha is equal to r over 2. And that gives us moment generating functions for the chi-square distribution that take the form 1 over 1 minus 2t to the r over 2 power for t less than 1/2. The chi-square mean and variance can be found from the mean and variance of the gamma distribution. In the gamma, the mean was equal to alpha times theta, and the variance was equal to alpha times theta squared. Substituting one more time, theta equals 2, alpha equals r over 2. We find that the mean of the chi-square distribution is equal to r, it's the number of degrees of freedom it has, and that the variance is equal to 2 times r, so twice the degrees of freedom. So let's take a look at how the degrees of freedom affect the shape of this chi-square distribution. You can see as our degrees of freedom are small, remember our degrees of freedom are equal to the mean, so we can see that our peak of this chi-square distribution, which is generally a distribution that's skewed to the right, is going to be down closer to 0. Whereas as our degrees of freedom increase, the peak of our distribution moves out to the right. You can notice also that the actual peak of the distribution is not at the mean. This is because it is a skewed distribution. So remember that the mean will be sort of pulled a little bit towards the tail, and you can look at the relationship here. Also notice one other thing, that as the degrees of freedom start to get large, we can see that this distribution starts to look a little bit more mound-shaped and less skewed. So that's another important thing to notice. Next, I want to talk about how we can use the chi-square table, which is in Appendix B, Table 4, to find probabilities with a chi-square distribution and to also find percentiles with a chi-square distribution. So suppose that X has a chi-square distribution with 9 degrees of freedom, and we want to find the probability that X is less than 3.325. Now our table here shows us in this part probabilities that the random variable takes on a value less than X, and the X values are in the body of the table. So we know we're going to be working with 9 degrees of freedom. We're going to be working in this row of the table. See here, are the degrees of freedom. In that row, we find the value that we're looking for, 3.325. There it is. And then we look up the column to find the probability. And we see the probability that X takes on a value less than 3.325 is 0.05. Let's try another example. Here, we're going to find the probability that X takes on a value larger than 16.92. Again, we're working in the 9 degrees of freedom row. We find the value 16.92 and follow it up. This tells us that the probability that X is less than 16.92 is 0.95, but we want to know the probability that it's more than 16.92. We're going to subtract from 1, and we can see that the probability that X is greater than 16.92 is 0.05. Now let's find the probability that X takes on a value between 3.325 and 16.92. We find the two values in the row for 9 degrees of freedom. And we're going to take the probability that X is less than 16.92 and subtract from it the probability that X is less than 3.325. And we're doing this, if we look at, sort of draw ourselves a little sketch, we can see that the area to the left of 16.692, that's our 0.95. We need to take away the part that's less than 3.325, and that's going to leave us with 90%, 0.90 in the middle. Now we can also find percentiles with the chi-square distribution. Here it's asking us to find the value of X that has area 0.975 to the right. So just drawing a quick sketch, we're going to find this cutoff point here. This is going to be our value, and we're finding 0.975 to the right. And that's what this portion of the table gives us. So we need to work in the column, the row with the right degrees of freedom. So here's 9 degrees of freedom. We want 0.975 as our area to the right, so we find that up here. And then we go down the column, and we can see that the value of X that has 0.975 to the right is 2.700. One more example. We'll do this again. Here we're looking for the value of x that has 0.01 to the right. So we find the place where our 0.01 intersects with our 9 degrees of freedom. And it gives us a value of 21.67. That brings us to the end of the videos for this week. Next week, we will be studying normal distributions. Have a good day.